Hello Pre-Calc PC. Today we are talking about unit vectors and forces. And you may ask, what is a unit vector? Well, a unit vector is a vector in the same direction as the given vector, but with a magnitude of 1. So remember, you can think of our magnitude as like our length, or we're going to see some more application with what magnitude really means over the next few days. But for now, in terms of if you're thinking a vector as an arrow, it's really the length of that arrow. So going in the same direction, but with a length or magnitude of 1. So we have two formulas that are really helpful to figure out what unit vectors are. The first says that the unit vector is just the original vector divided by its magnitude, because when we do that, we'll get the same vector but with a magnitude of 1. And then another option is just if we were to multiply the magnitude over, we can say the original vector is the same as the magnitude of that vector times the unit vector. And this should make sense because the unit vector has a magnitude of 1, so we multiply by the magnitude that we want in order to get our new vector. Okay, so those are two different formulas, but really they all come from the same thing. So let's give this a try. Find the unit vector having the same direction of a given vector. So let's just make sure we understand what this means. Our given vector, which you could also put the arrow there, is 5i. This means that we are just going in the I direction. Okay, it looks like this. All right, now first thing we're going to do is find the magnitude of this vector, which is the length. All right, and the magnitude is just our x component squared plus our y component squared, and because there is no y component, it's really just square root of 5 squared, which is 5. That means that our little arrow here has a length of 5 in the x direction. All right, so our unit vector, to find that, all we have to do is take the original vector, which is 5i, and I like to put the little hat on it, and we divide it by its magnitude, which just gives us I. Okay, so our unit vector is I, or if you want, you can say your unit vector is 1, 0. The 0 is there because, again, we do not have a j component or a y component. All right, let's try another one. So here we have this vector, negative 5i plus 12j. So remember, negative 5, that means you're going in the negative x direction. 5, and then up 12. And we have this arrow right here. Okay, that's basically what's happening. So in order to find the magnitude, which is the length right here, we're basically just doing Pythagorean theorem, right? So your magnitude of v is the square root of 5 squared plus 12 squared. And you might recognize this as a special right triangle. This should just give you square root of 169, which is 13. Okay, so that's the magnitude or the length of this little arrow right there. So to find the unit vector, we just take our original vector. This shows us the direction that it's going, and we divide it by its magnitude. And that will give us this guy, negative 5 over 13i plus 12 over 13j, or you could write this like this, negative 5/13, 12/13. Either is fine. All right, so just to be clear what we just did here, what this is supposed to do is it is supposed to give a vector going in the same direction as this vector, but with a magnitude of 1. All right, so if you look at it, it's really similar. It's just divided by that 13. So we would go negative 5/13 to the left, and we'd go, or 5/13 to the left and 12/13 up. So you would have that same direction. All right, see how it's overlapping the original line? But let's see what happens when we take the magnitude of this guy. Okay, so magnitude, again, we just add the x coordinate squared plus the y coordinate squared, because it's basically Pythagorean theorem. That's going to be 25 over 169 plus 144 over 169 which is 169 over 169, which is 1, which the square root of 1 is 1. Okay, so we have achieved what we set out for. We have a vector that's going in the same direction as our original vector, but now the magnitude or the length is just a 1. Okay, so that's what we just did. That's why the arrow is super tiny there. All right, so now let's try to go backwards. We're going to find a vector W whose magnitude is 3. Okay, so the magnitude of W is 3, and whose component in the I direction is equal to the component in the J direction. Okay, well, they didn't tell you what the I component and J component are. They just told you they're equal. So you can kind of create a vector that you want that has that I component equal to the J component. So I'm going to call this vector V. And I'm just going to call it I plus J. All right, they're both 1s here, so their I and J component are equal to each other. Now, this is not the vector I want because this is not going to have a magnitude of 3. Okay, the vector we're looking for, W, has a magnitude of 3. Look, I'll prove it to you. I do the magnitude of my vector that I just found here. That would be square root of 1 squared plus 1 squared, which is a root 2. Okay, so the vector that I just created has a magnitude of root 2. I want my magnitude to be a 3. Okay, but we can use this. What I can do is I can create a unit vector, and I know that a unit vector has a magnitude of 1. Okay, now again, I know that 1 isn't the same as 3, but bear with me here. Okay, the unit vector takes our vector and it divides it by its magnitude. Okay, so I just created a unit vector here. Okay, that's my unit vector. This guy is in the same direction as V and W. Okay, W is what we really want to find, but magnitude of 1. All right, so again, let's review this because this is a lot. We are ultimately looking for vector V. We were told, or excuse me, vector W. That's W. We are ultimately looking for vector W. Vector W has a magnitude of 3, which we haven't accomplished that yet, but its I and J component are equal. Okay, so what we did instead was, well, we don't have a magnitude of 3, but let's create a vector that has that same direction. The I and J component are equal. Okay, so this is another vector going in the same direction as W, but with a different magnitude. By dividing by its magnitude, we've now still accomplished that. This unit vector is still going in the same direction as W, but it has a magnitude of 1. So now what we get to do is we can use this formula over here. We're looking for vector W, and in order to do that, we can just multiply our unit vector by the magnitude we want, which is 3. This is already going in the same direction that I want, it just has the wrong magnitude. So in order to find vector W, I just need to take 3, which is the magnitude I want, and multiply it by this unit vector I've created. And that will give me 3i over root 2, or 3 over root 2i, plus 3 over root 2j. That's an I again, j. All right, and this will be your final answer. Okay, so again, in order to find the unit vector, we take our vector and divide by its magnitude. And then what we can do is that unit vector, since it has a magnitude of 1, I can just go ahead and multiply that by the magnitude I want, 3, to get vector W. Good times. All right, next, we're going to write the vector V in the form AI plus BJ, given the magnitude and the angle it makes with the positive x-axis. All right, so let's take a look at this. The magnitude is 8 and alpha, which is our angle, is pi over 4. So that would be like here, and this magnitude is 8. Okay, well, we're looking for our I and j component, which is really our x and y component. So this should look really familiar with polar form. We're just looking for x and y. Remember before, x was r cosine theta and y was r sine theta? Well, this is really the same thing, except we're not calling 8 our radius anymore. 8 is our magnitude. So x is really our magnitude cosine theta, and y likewise is going to be our magnitude sine theta. All right, so I guess I'll use my notation here. Magnitude cosine theta, magnitude sine theta. All right, so let's go ahead and find it. X is equal to 8 cosine pi over 4, and y is equal to 8 sine pi over 4. This is the same thing as polar, except for now we're calling what that radius was our magnitude. Cosine of pi over 4 is just root 2 over 2. So I have the same thing for both of these guys, which should simplify to 4 root 2 and 4 root 2. All right, so you have two ways to write this. We can either say that vector v is 4 root 2I plus 4 root 2j, or you can say vector v is 4 root 2, 4 root 2. Just make sure you have angle brackets here, not parentheses, okay? This is a vector, not a point. All right, let's go ahead and try the next one. This time we have a magnitude of 3 and our alpha is 240. Okay, so 240 would be over here, right? And we will have to find our reference angle. Reference angle is how many degrees we are from our x-axis, which was at 180 degrees here. So that means that I'm 60 degrees away. The reason we want to find that is because we are going to have to find sine and cosines. So we need to know what our reference angle is so we know what our sine and cosines are. All right, so again, x is our magnitude cosine theta. And you're still doing cosine of 240 even though our reference angle is 60. And y is our magnitude sine theta. All right, so a cosine of a 60-degree angle is a 1/2, but I am in quadrant 3, so it's going to be a negative 1/2. So that's negative 3/2. And sine of a 60-degree angle is root 3 over 2, but again, I'm in quadrant 3, so that's going to be 3 times negative root 3 over 2, which is just negative 3 root 3 over 2. Okay, and now we can write our vector. You can either write this as negative 3/2 I minus 3 root 3 over 2j. So there's option 1. Or you can go ahead and write this with your angle brackets, negative 3/2, negative 3 root 3 over 2. And again, both of these are completely acceptable. It's like set notation versus interval notation. It doesn't matter. You can write it either way every time. Even though it says AI plus BJ form, this is still that. Okay, so either is completely fine. All right, next, a man pushes a wheelbarrow up an incline of 20 degrees with a force of 100 pounds. Express F in terms of I and J. So this force of 100 pounds, this is actually representing our magnitude. It's how large of a force it is, which up until this point, we've just thought of as the length of our arrow, but now we're actually looking at this in terms of a real context. So that force of 100 pounds is our magnitude. Okay, so just to give you a little picture here, we've got a 20-degree incline. That's not actually 20 degrees, but we'll go with it. And our magnitude here is 100. Okay, so we are just finding, when it says express F in terms of I and J, it's asking you for your X and your Y components. So we're really doing the exact same thing here. So again, X is just your magnitude cosine theta, and your y is your magnitude sine theta. And this we will have to use our calculator for. All right, I had to go ahead and pull my calculator up. We do want to make sure we're in degree mode, which I am not, so I will switch that. Okay, and then we can just type this in. 100 cosine 20 and 100 sine 20. And then we'll always round to the nearest thousandth, so a 93.969 and a 34.202. Okay, and then you can go ahead and write it either like this, or we can write it like this, 93.969i plus 34.202j. So that is telling you the x distance and the y distance that it was moved over and up. There you go. All right, so the last thing we're going to talk about today is resultant force. We are not going to worry about static equilibrium today. So what is resultant force? Well, it's when we have combined forces acting on an object. And we're going to look more at this in our next lesson. Today is just going to be an introduction. So generally, to find resultant force, we are going to add our forces together. And in order to do this, we must have our forces in component form. Okay, which means you need to have your I and your J component. All right, so for example, if you come down and look at number 7, find the resultant force of the given diagram. This is not in component form yet. We just have our magnitude and we have our theta. We need to actually do our magnitude cosine theta and magnitude sine theta to find our I and J components, and then we can actually find the resultant force. All right, so let's go ahead and do this. One thing that I want you to notice is that your reference angles are already here for you. 45 degrees, that's our correct angle, but 60 degrees, this is in quadrant 2. So even though this is the reference angle, we still need to know how many degrees we went to get there. So if that's 60, this is going to be 120. All right, so the reason that's important is when we do our force 1, and we find our x and y component, again, which is magnitude cosine theta, magnitude sine theta. Our magnitude is 70. Cosine, we're actually doing cosine of 120, not cosine of 60. And that's because the 120 puts us into the correct quadrant. And then magnitude sine theta. Now I'm writing this a little differently than I did above. And you can still do this if you want. Instead of writing the x equals magnitude cosine theta, y equals magnitude sine theta, and then putting it in component form, I'm just starting with it in the angle brackets. And now I'll go ahead and simplify. All right, so cosine of 120, again, your reference angle is 60. We know that cosine of 60 is a 1/2, but we are in quadrant 2, so it will be a negative 1/2. All right, and sine of 120, again, reference angle is 60. So the sine of 60 and 120 is a √3/2. We are in quadrant 2 where sine is positive, so this is just a √3/2. And now I can simplify that. So I'm going to get a vector of negative 35 and then 35√3. Okay, so that is force 1. Now I'm going to go ahead and do force 2. Okay, so force 2 is in quadrant 1, so I don't have to worry about converting my angle at all. It's just 45 degrees. So again, this is magnitude cosine theta and magnitude sine theta. And cosine and sine of 45 is √2/2. And so that means that when we simplify this, we're going to have 15 root 2 and 15 root 2. And that is our force 2, which you can put arrows over if you want. All right, so now how do we find the resultant force? All you are going to do is you are going to add these together. So we have, you can even add them just like vertically. So there's vector 1 or force 1. Here's force 2. You are literally adding them together. So the x components will add and the y components will add. So negative 35 plus 15 root 2, that doesn't do anything. So it just looks like this. And 35 root 3 plus 15 root 2, those cannot combine either. So it's written like this. And you can either leave your final answer like this. I'm going to put it as F1 plus F2. Or you can write it, really want to make that an I for some reason. Or you'd have to write it like this, negative 35 plus 15 root 2 I plus 35 root 3 plus 15 root 2 J, which I feel is super obnoxious looking. So I would just recommend using the angle brackets. Okay, so there you go. That's how we find resultant force. And over the next few days, we will see why resultant force is really important. All right, I hope you have a great day. Bye.